Okay.
Okay. Hi, good day, good morning, good afternoon, good evening to everyone, wherever you are. It's our pleasure and honor to host you all. We wish all of you and your loved ones are doing great at the same time attending scientific events like this one. Both Sebastian, Geiger, and myself are delighted to have all these fabulous keynote speakers to make this channel quite a successful one and being so well received in the community. We are getting beyond 1,800 subscribers, and this is quite encouraging. Welcome to the webinar of 4th of February, the 5th webinar of this year, 2021. Today we have the pleasure and honor to host Professor Zuleima Karpyn from the Penn State. Thank her for graciously accepting our invitation and being available, despite I would say she would be so busy and many teaching and administration as well as teaching research also obligations as well. So thanks a lot, Zuleima, for accepting our invitation. I would read a few lines about her and then we would have the lecture to start soon. Zuleima is Professor of Petroleum and Natural Gas Engineering and Associate Dean for Graduate Education and Research in the College of Earth and Mineral Sciences at Penn State, the Pennsylvania State University. She specializes in multi-phase flow and transport in porous media and digital rock physics. Areas of application include broad range of applications include reservoir characterization and engineering, enhanced oil recovery, environmental remediation, and carbon sequestration. She holds a BSc degree in chemical engineering from Universidad Central de Venezuela, and MSc and PhD both in petroleum and natural gas engineering from the Penn State, so not so far from where she works today. She is a recipient of the 2008 Faculty Early Career Development CAREER Career Award granted by the National Science Foundation, the 2010 Wilson Award for Excellence in Teaching, 2016 Fulbright US Scholar, the list goes on, 2008-9 Big Ten Academic Leadership Flow, and many, many, including Energy Simulation Chair in Fluid Behavior and Rock Interactions. She has also served as Associate Editor of the Society of Petroleum Engineers Journal, SPEJ, quite a prestigious journal in the geoscience field, Assistant Editor-in-Chief of the Journal of Petroleum Science and Engineering, another very good journal, and Associate Editor of Transport in Porous Media as well. So this is quite a significant contribution and service that she is offering to the community at the largest scale. Thank you very much, Zuleima, for being here. To the audience, please visit her page, a scholar page, to study her research outcome, most of them. Please note her lecture would last for about half an hour, and like always, followed by questions and discussions at the end. Sebastian would share the discussion session, like always. Text your questions, and as soon as you have a good question to raise, please do type it. It might trigger other questions as well. And we are looking forward to host a quite lively discussion session at the end as well. So without any further ado, it's our pleasure and honor to have you, Zuleima, with us today. Thank you again very much. We are all looking forward to hearing your lecture.
Thank you, Hadi. Can you hear me well?
Very well, pretty well.
Hello, everybody. Well, thank you again, Hadi, and thanks, Sebastian, for first, creating this platform for the geosciences and geoenergy community to have this opportunity, and thanks for the invitation to share my work through this channel as well. This is work that I've done within my research group at Penn State. I will be presenting to you some contact angle measurements and some evidence of wettability alteration in porous media. I'm your speaker today, but I would like to acknowledge the true effort behind these slides, especially Miral Tafik, a former PhD student in my group. She's now at Chevron. The vast majority of what I'll be presenting today is part of her work. Also, thanks to collaborators, former students, and supporting companies, for this work. I want to start my presentation from a shared understanding that wettability describes the preferential affinity of a liquid to maintain contact with a solid surface. It's a manifestation of a balance of forces acting on the surface of a liquid that is in contact with a solid. We're talking about adhesive forces, cohesive forces. These cohesive forces are the forces that are in intermolecular forces of attraction within the body of fluid, and the adhesive forces are now attractions between the fluid and the solid surface. In the case of, for example, noted here in my slide, where the adhesion, if it were to be stronger than the cohesion, then what would happen is that the surface of the liquid would expand in response to the resultant net force. How much is that surface going to expand? It depends, or is dictated by surface tension. And then what we can see is that if there's a strong adhesion, as we see in this case, that would lead to a capillary rise, as indicated here, or also as an indication of the liquid wetting the solid, or vice versa in the case where the cohesive force will be stronger than adhesive forces. So that's kind of the baseline that I wanted to establish. Now, how far will the liquid rise depends on conditions of hydrostatic equilibrium, the balance between, how strong is that adhesive tension pulling the fluid up versus the weight of the column of liquid, until they balance each other. And because in this case, the adhesion is acting upwards, extending the height of the liquid column, then what would happen is that there would be a pressure differential across this interface, that the pressure that we find here within the column of liquid right at the interface within the liquid will be lower than what we find in the air phase. And that pressure differentials, or capillary pressure, is given by Young-Laplace equation. And what is important here to note is that effect of that capillary drive, that capillary pressure and that wetting affinity can serve as a driving mechanism for flow in porous media, like a spontaneous capillary movement. Wettability can also have a strong influence on the retention of fluids in porous media. How do we quantify the strength of that wettability? We do that through contact angle measurements. The standard is such that if we have a contact angle measure through the liquid phase, if it's greater than 90 degrees, we're referring to a non-wetting liquid. If we have a contact angle that's less than 90 degrees, we're looking at a wetting angle. And that's, in essence, how we quantify. There are multiple standard methods for measuring contact angles. Those are, some of them are listed here: sessile drop, optical tensiometry, force tensiometry. What's common through all these standard methods is that they use homogeneous flat surfaces to represent the solid phase over which that drop of liquid, or that contact with liquid, is exerted. And that is a problem when we try to translate this effect of wettability to porous media, where these methods may not be able to capture the full complexity that we find when these interfaces are formed within a porous structure. So that creates a problem. And that is that traditional contact angle measurements are unable to capture the full range of contact angles that are representative of wetting conditions found in porous media. And because of that, they're also unable to consider the effect of chemical heterogeneity given by mineralogy, pore topography, roughness, and these are really inherent properties of a porous medium, or perhaps even capture the evolution of these wetting conditions as a result of changes on affinity between this liquid and the solid. This has important implications for flow dynamics, for fluid displacement, for trapping. For example, as we try to estimate permanent trapping of CO2 during geologic sequestration jobs, it's important to be able to have accurate estimates of the capacity to have that retention of CO2 in place. Another, good example is, the impact that wetting properties has on the residual oil that is obtained at the end of an improved or enhanced oil recovery process. At the same time, some conventional modeling approaches also treat contact angle as a single characteristic value rather than a spatial or temporal distribution. And what I'm trying to do here is to address that gap with the help of X-ray computed tomography. So X-ray computed tomography is a non-destructive technique for three-dimensional imaging of a broad range of opaque materials. At Penn State, in the Center for Quantitative Imaging, when we have this type of instrumentation, the cabinet we have is large enough that it can be used it can accommodate concurrent imaging and core flooding at controlled conditions of pressure, temperature, etc. The instrument we have, or the one that we're referring here to in this slide, because we have another one as well. In this case, the instrument can provide image resolutions that range from a single micron to a fraction of a millimeter. The data output is quantitative, and therefore that makes it very suitable for quantitative analysis, and numerical modeling as well. The applications for this type of technique are very broad. Essentially, just internal inspection of materials that you could not otherwise see inside without destroying it. There are several of us around the world working in this space of using this type of technique for digital rock physics, and that's what I'm presenting, for you today. Here's one example of the type of visualization that I'm referring to. It represents in red a three-dimensional oil blob that is trapped or resides within a glass bead column, and I think presents the ability to have a three-dimensional mapping of fluid occupancy within a porous material with great accuracy. And this is not only useful to obtain saturations, but you can get information about connectivity, topology of those fluid bodies, surface areas, and we've done some of that in the past as well. Some 10 years ago, approximately, we did some core flood experiments using these glass bead columns to try to inspect an entire population of residual blobs of oil after a water flood or a water injection. We were looking at over 10,000 disconnected oil blobs within that column. In this figure, what we see here on the vertical axis is the vertical position along the length of the core that we use. On the x-axis, we have the size of the oil blobs that were found. Each dot represents a single individual blob that we were able to see, and 5 of them were selected for just for representation of where they are within that column. The mean blob size was, in this case, 0.15 cubic millimeter in volume. Most blobs had an aspect ratio about 1.5, meaning maximum dimension of the box that encapsulates that body to the minimum dimension. So they were not significantly elongated. But what became really clear with this exercise is the relevance of the structural features of the porous medium in prescribing the shape that these blobs are going to have, how big they're going to be. And these led us to want to then overlap the variable of wettability. What if we change wetting conditions? In this case, this was a glass bead column, so it's strongly water wet. So we proceeded a few years forward with a series of core flood experiments where we had bead columns fairly similar to the ones I presented before, with beads of approximately 0.7 millimeter in diameter. But in this case, we had some uniform and mixed wet cores with different contrasts in wettability. So we had uniform cores that had an entire column of glass beads, an entire column of plastic beads, and we had some that had a mix of plastic and glass beads, and another one that had a mixture of glass and coated glass beads to create different contrasts in that mixing of wettability. The stages of the experiment were very similar. For all cases, we start with number one here with the imaging of dry conditions to have a good mapping of the pore structure. Then we pre-saturate it with the wetting phase. In this case, this image corresponds with the plastic bead pack. We pre-saturated with the oil phase, that in this case was kerosene is what we use. And then inject water or brine until we reach a residual oil saturation, and then oil again to a residual brine saturation. So that process allowed us to then extract, similarly, information about fluid occupancy, how they're distributed, how saturations are distributed, and take a closer look at what's happening inside. In this diagram, we see on the first figure, it's a vertical profile of residual saturations. The lighter red or the pink corresponds with the oil phase, kerosene. So this is this pink profile would be residual kerosene saturation at the end of a water injection in the mixed wet bead pack. And from this figure corresponds with the column that has a combination of glass and plastic beads. We see the glass beads in dark blue, the plastic beads in dark red. The fluid that has the more affinity with the plastic being the oil, then is lighter pink, and the fluid that had the greatest affinity to the glass is lighter blue, being the brine. So as I was saying, the vertical profiles corresponds with the residual saturation of brine in blue and residual saturation of oil in pink at the end of each corresponding displacement. And you can see both of them here. So at the end of kerosene injection, we see some residual water inside the pore space. At the end of the brine injection, we see some residual kerosene in place. And we can begin to appreciate that the data gave us enough quality and resolution to try to look at in-situ contact angles. So that was our first attempt to try to get measurements of that type on porous media that are synthetic, they're regular, very large pores, grains are spherical, so the most favorable conditions to be able to do that. What was particularly useful also of this data set is that we had explicit distinction of the solid surfaces. So we knew exactly where the glass were, we knew exactly where the plastic was, and we could therefore associate contact angles with the sites or the solid sites where they were in contact, and you'll find how that was useful down the road. So in collaboration with Catherine Kleiss at Sandia National Lab, she developed an algorithm for contact angle measurements for these more kind of simpler geometries, but still three-dimensional. And that allows us to then construct a data set of contact angle measurements with different sites and for different columns and displacements. And this is what we obtain. So in this case, I'm presenting a statistical distribution of contact angle measurement obtained from both uniform wet columns or cores and also the mixed wet core that had plastic and glass. These statistical distributions account for thousands of contact angle measurements. These contact angles were measured at residual saturations on the plastic surface or the glass surface. So each of these corresponds with residual states, be it residual water or residual oil. The figure on the left here is for uniform columns, and the one on the right is for the mixed columns. Keeping the same nomenclature, the reds represent the plastic solid surface and the blue represents a glass solid surface. So these are in blue, these are the contact angles that were measured at residual saturations in contact with the glass surface, and the reds are residual saturations and contact angle measurements at those residual saturations on the plastic surface. In this particular case, we can see that the median contact angle calculated for this uniform red plastic bead pack after the first displacement was in the order of 165 degrees. For the same surface, after a second displacement, that contact angle became a little lower, as we can see a little shift in the distribution. It became 150A. The contact angles measured on the glass surface, they shifted from approximately 54 to 66 degrees. In the case of the mixed wet cores, also at residual saturations, what we see, the contact angles that were measured on the plastic surface, they changed from about 159, the median, to drastically to about an 82 degree from the first displacement to a second displacement. And the contact angles measured on the glass surface, they changed from about 50 degrees to 81. So they both shifted significantly to a more of an intermediate state. The wetting characteristics that we saw, typically they tended to just a less strong wetting state. So we started with something that was significantly oil wet, it became a little less oil wet, it was significantly water wet, became a slightly less water wet as measured by our contact angles. In the case of the mixed wet cores, we saw that after the second displacement, there was a significant shift, and the difference between the contact angles we measured on the glass surface or the plastic surface was almost indistinctive. That these contact angles were very, very similar. We think that happened because, or that this effect was thought to be due to the fact that at the end of that second displacement, the residual blobs that were formed over which we measure contact angles had a better connectivity and ended up being in contact with both water surfaces and oil in plastic surfaces. And then at that equilibrium, those contact angles ended up being fairly comparable. But I think what was perhaps an important takeaway from this exercise was that we can see the potential to extend these type of measurements, or the idea of having distributions of contact angle measurements, to more complex structures, and perhaps even invite the opportunity to monitor wettability alteration now in a natural porous media, because this was all under a synthetic system. So that's how we came to perform these experiments of microcore floods in carbonate cores. The objective for this body of work was to gather evidence of wettability alteration during chemically tuned water flooding using carbonate cores. In particular, we wanted to investigate the effect of oil chemistry on the mechanisms that influence the performance of chemically tuned water flooding, beyond total acid number as an indicator of what would be successful. So we created oil mixes that had the same total acid number, but they had a different chemical nature. We use Indiana limestone cores of 17 to 19 percent porosity, very small cores, to really maximize our chances to be able to obtain nice curvatures of fluid-fluid interfaces within a rather complex pore structure as carbonates often have. The fluids that we use two types of oils, and these two oils were prepared with a common base that was formed by a mix of hexadecane and diiododecane at a 13% by weight, to be used as a contrasting agent to increase the distinction of the oil and the brine phase when it came to time for us to do image processing. In addition, we added a surface active component that is the one to which we attribute most of the potential for altering wettability and responding to wettability alteration through chemically tuned water flooding. The two surface active components that we used were two carboxylic acids, acetic acid and decanoic acid. So we formed with those two different oil mixtures. These two mixtures were prepared to have the same total acid number, as I said before. The brine phase, we also prepared two mixes, one at high salinity to represent formation water to establish initial conditions, but then use a second brine as our low salinity, chemically tuned brine. Significantly lower ionic strength. You can see that the composition on this table. Selectively, we purposely made the magnesium and sulfate ions fairly high on our chemically tuned brine, and we compensated some of the other ions to maintain a lower ionic strength. And that is because magnesium and sulfates are considered to be a significant in that process of being able to alter wettability as a strong, potential determining ions, as described also in the literature. So we had these two oils, and we displaced them with a low salinity brine after having established initial conditions with a formation brine. The process goes as follows. We have our core sample. We vacuum saturate the sample with this high salinity brine to represent our formation brine. At that point, we could obtain some permeability measurements. That became, those permeability measurements became actually more meaningful as we did a comparable experiment at a larger scale using a kind of Darcy scale set up to measure recoveries in parallel to this. And I'll explain that a little bit more, towards the end. But the process is still, the same. We pre-saturate with our high salinity brine. We have an opportunity to inject single phase through the sample. Then we inject one of the two oils, either acetic acid or the decanoic base oil. Then as we do that, we go through a process of aging. We're injecting oil continuously for 7 days at temperature. And after that is when we believe to have our sample at the proper initial conditions to proceed with the chemically tuned water flood. So at that point, we inject 10 to 15 pore volumes of the low salinity chemically tuned brine. We inject at select stages of we scan at select stages of the experiment. We create data sets of what the dry sample looks like. And then also when it's saturated, fully saturated with brine, then saturated with oil, and then add residual saturation conditions. And on the right, you can see two sample slices of the dry core and the saturated core. And you can see already really the complexity of the pore structure is significant. It makes it really an interesting and challenging problem to work with. We also did on the side some sessile drop contact angle measurements of space-time, not only for the acidic treated cores, but also the decanoic treated cores and several other ones. And we could see that the core, at least through these measurements of preliminary measurements of sessile drop contact angles, and these are measured through air, by the way. I think it's important to mention, different from what we encounter in reality within the pore space that is oil brine. But still, I think it gives us a baseline of expectations of what we would have in the case of the cores exposed to acetic acid. We can see that the sample exhibits overall a water wet state. You have a contact angle slightly lower than 20 degrees after the sample had been aged with that oil and after the treatment with the low salinity brine injection. In the case of the decanoic mix, we see that through the aging process, we reach a preferential oil wet state. And after the injection of low salinity brine, that wettability changed slightly. At least this is the preliminary measure of what we've seen. Then going to the detail of the type of data that we obtain from our micro-CT imaging, we have here a typical data set from the microcore flood experiments. We can select volumes of interest where we find interfaces that are could be suitable for contact angle measurements. So we work with sub-volumes of the entire sample. The sample is very, very long, and that gives us a chance for us to identify multiple sections where we can take contact angle measurements. The procedure that we follow for image processing is fairly standard for a lot of the work that we do in data image analysis for pore structure applications, but I'll still describe it here for the sake of our broader community and audience. We start with, having data sets from, the stages that are relevant from the experiment. In this case, I'm presenting some stack of dry slices in a stack of saturated sample slices. We go through a process of filtering, cleaning, enhancing the quality and the contrast of the image, and you can see that here we have good representation or mapping of the pore structure, and here we can see the two faces occupying the pore space. We then go through a process of registration just to confirm that both volumes can spatially correspond with each other. Because that ends up being convenient in the process of identifying what's the pore space and what is not. So we go through that process of registration. We tend to go through the process of imaging in a way that we don't disrupt the sample to try to avoid any movement. But in the cases where you have really fine resolutions, in this case, in the order of 2 micrometers resolution, a minor movement, even changes in temperature within the cabinet of the scanner can lead to a shift in these images. So once the samples or the volumes are registered with each other and they correspond in location, what we do is that we can identify the pore volume from the dry images that provide the best quality data set for us to detect what is the pore structure. Once we have that detection of the pore space through segmentation of what is pore and what is rock, then we can superimpose that template on top of the saturated images and really simplify the process of segmentation of faces here. If we're doing a segmentation straight from this data set, which means identifying what's rock, what's brine, what's oil, we'll be doing a 3-phase segmentation: the oil, the brine, and the solid. But if we have intrinsic or independent knowledge of what's a pore space or not, we can superimpose it and reduce our problem as one that is a binary decision. Is it oil or is it not? Or is it brine or is it not? And that really simplifies the process of segmentation. And once we have that, we can apply it to the entire 3D volume and have a really sharp distinction of families of groups, whether it's oil or rock or brine. And it would end up with images like this. This is a particular subsection extracted from the sequence of scans and experiments on the decanoic acid mixture for the oil phase. We have images from before the sample was aged. So the sample started in what would have been primarily mostly a water wet state, as suggested by the interfaces between the black and the blue in this first image on the left. Post-age, we see a significant change on the contact angle and these curvatures, indicating a significant change in wetting conditions to one that's much more oil wet. And this is something that we wanted to achieve through the process of aging, and that was successful. Then after the injection of the low salinity brine or post-chemically tuned water flood, we can still see some of that oil wet state in the distinction between the brine and the oil phase. This is the type of data set that now we can use to explicitly go and measure some of these contact angles in situ. And the process consists of identifying fluid interfaces. So this is a body of oil in contact with either rock or brine. We can then identify where the contact rims are, or the 3-phase contact lines over which we can measure contact angles in 3D. And that's how we proceed. By identifying those contact lines, then we can really position ourselves not only on the plane of scanning, which is the XY ortho slice. I think what's critical here is, because we have a complex topology within the porous sample, is that we need to find the proper orthogonality to measure contact angle through those fluid interfaces. And what I'm trying to display here in this slice is that, yes, we identify our body of oil. In green, we identify those contact lines, or those points where there's contact with the oil, with the brine, and the solid, that are sites over which we could measure contact angle. And then the repositioning of a slice over which we can estimate that contact angle. In this case, that reoriented slice gives us a contact angle of about 35.5 degrees. We can do that in multiple locations along the same ring, the same rim of contact. We can do that over multiple bodies and really create a broad range and a very wide range of sites over which we can get estimates of contact angle to have a much more complete signature of a wetting state for a particular sample. And this is what we represent here. This is a contact angle distribution for and the acetic acid oil, that shorter chain oil mix. This is the original pre-age state of the sample in terms of wettability. So it's primarily strongly water wet in its pre-age state. After exposing it to the oil through several days of aging, dynamic aging process, we see a very, very small shift in contact angles towards a slightly more oil wetting state, but still fairly water wet. Then that sample is subject to the chemically tuned water flood, and we can see down a shift back, very slight, very minor. So we didn't see in this case a significant shift in wetting conditions by having first aged the sample and then introduce a low salinity brine. So the rock was not very responsive to changes in this case after in the presence of this particular oils. We did the same with the decanoic oil with its oil base. The contact angle distributions of the pre-age state is this one, primarily water wet, but with more of a bimodal distribution of contact angles. After the process of aging, there's a significant shift in the characteristic and a contact angle distribution, becoming significantly oil wet, much more susceptible to change in this case. And I think that susceptibility to having altered wettability through the aging process is also then reflected back as we went through the process of chemically tuned water flooding, when we then see then a shift back to a pre-age state. We see significant changes in this case. We see that the wetting state is also characterized. It's very interesting in terms of that distribution, where a single value of a contact angle might not have been fully capturing or characteristic of the wetting nature of the sample. We, as I mentioned earlier in the presentation, these experiments that we did with the microcore flood experiments were also repeated at a Darcy scale to look at permeability, to look at displacement and recovery factors, and see if we saw any type of correspondence of these kind of pore scale indicators of wettability alteration versus some of the more larger core scale indications of effectiveness in change in wettability. And this is what we observe. So I'm putting here on the left is the summary of the contact angle distributions for the acetic acid at the top and for the decanoic acid at the bottom, as they went from the having been aged and then changing to after chemical tuned water flood in yellow for both cases. So we see very small change in the distribution of contact angles in the case of the acetic acid, and we see a much more dramatic shift for the case of decanoic oil. In terms of the recovery factors at the lab scale where we conducted these experiments, same conditions, same oils, same rock, larger of course because it was such a different scale. We see that the displacement process here is very different from them. In the case of the acetic acid, a lot of almost piston-like displacement. We get a lot of recovery very quickly and then plateau very fast. We get what we're going to get very, very quickly. In the case of the decanoic oil, what we see on one hand, some evidence of a process of alteration of the wettability with exposure to the low salinity brine. We believe that that's also an indication of a more gradual process in being able to recover additional oil from the sample. So I think this for us, this was quite meaningful and able to see differences at one scale that could be very well explained or supported by what we see through these pore scale observations. The contact angle distributions that we see here were also interesting for us because suggest that perhaps there's some localized alteration of wettability, where we see maybe a range of really small contact angles and a range of some of the larger contact angles that may have not been reached perhaps with the same effectiveness that they did before. And we found that to be an important attribute of capturing a distribution of contact angles rather than a single value characteristic of the whole. So with that, I get to my summary of findings where I presented to you hopefully evidence that wetting properties are susceptible to displacement cycles. We saw that to some extent in the synthetic cores and also in these later carbonate cores. The nature of the surface active component that we have in the oil can play a major role in the success or what we expect to obtain from a chemically tuned water flood. And this is, of course, a combination of the nature of the chemistry of the brine, the chemistry of the solid, the chemistry of the oil itself. But they play a very important role. In the literature, we find much more emphasis paid on the composition of the brine to calibrate and to engineer this chemically tuned water flooding processes. Perhaps less attention being paid to the chemistry of the oil itself beyond total acid number, which is typically used as a screening indicator for whether chemically tuned water flow would be more or less successful. In situ contact angle measurements confirm wettability alteration, and we could also see some effects that could be tied to the shape of the recovery curves from chemically tuned water flooding experiments. The distribution of contact angles, we saw that it could vary significantly for a given wetting state. So a contact angle of 60, it's more than a contact angle of 60 degrees, for example. It could be really a representation of a lot of diversity in terms of contact angle distributions, and perhaps even attributed to different sites within the sample. X-ray microtomography offers a non-intrusive technique to measure contact angles in porous media, doing it in situ and with more representative sampling as well. I find also that I think it's very important to bring up the value of integrating also experiments or observations from different scales to try to build a more continuous story of how pore scale dynamics drive the manifestation of behavior at a larger scale, like recovery, like trapping, etc. And with that, I end my presentation. I wanted to thank everybody for your attention and also, my group in the lab. Thanks.
What a nice picture. We are all looking forward to these photos soon after this pandemic with the group as well.
Absolutely.
Thank you for putting this up. I hope all of them are doing great and are enjoying watching this very informative and engaging talk. I really enjoyed and learned a lot. Thank you very much for this. Sebastian.
Yes, thank you very much, Zuleima, for great talk, and thank you for giving the presentation. And so before we went live, we just reminded ourselves that the first time the two of us met was at a AGU conference when we were still PhD students, which was the odd year ago, but at least you have hardly aged since then. So on that cheery note, we have quite a few questions coming in and hopefully some more coming up shortly. To start with one from Soren, says, very nice talk. How accurate are the measurements for small contact angles, say about pi, 1/10 of pi or less, or very large ones, so close of pi? So that's the first question. The second one is, are the contact angles that you measure assuming static, so independent of flow speed, hysteresis effects, flow reversal, etc.?
Excellent. Very good point. Well, the accuracy of the measurement of contact angle is very sensitive to the resolution that you have in your sample, right? How many voxels across that curvature are you able to capture to draw the right tangent? For the cases that we have, I imagine it will be very difficult to measure contact angles that are very small, because identifying that interface of the liquid in contact with the solid, and that other interface of the liquid with the other liquid, if they're very close to each other, you intrinsically you have very few voxels to count, and then the gridding effect that you have will increase. So definitely, as you have a larger pore where you have a nice curvature, your accuracy will increase as you're narrowing your contact angle. Or if your pores are very small, then your resolution will suffer, and the quality of images of your measurement will suffer. We did some, as we were creating this algorithm for contact angle measurements, we did some sensitivity analysis that addresses that precise question, where we created something synthetic spheres to have a theoretical measurement of contact angle, and how your accuracy will change. And it could be ranging between 5% error to a 30-35% error, precisely because of what you said. The second part of the question, Sebastian, remind me what the second part was.
So the second one was if you assume the measurements to be
static or dynamic. Yes. Well, the measurements that we did using CT imaging were static measurements, because if we obtain these images during flow conditions, those interfaces will be moving, and that will create a blurred image, and that doesn't allow us to have the sharp interfaces that we need to make the measurement. So we are doing a dynamic displacement. We stop flow, we scan. The scanning itself takes a couple of hours, and that is done under static conditions.
Just a quick sort of side question from me there. So when you do, the scans take quite some time. So do you see some rearrangement of blobs of the phases that change your contact angle measurements?
Occasionally we see in the images blurred interfaces that we attribute to moving around. But the way we try to minimize the occurrence of those blurs or shifting of fluids inside the sample during scanning is by doing the experiment in a way that we try to reach some form of residual state, where we are achieved a point where the residual phase is as close as possible to being immobile, and in that point, just the rotation of the sample as you're scanning is not strong enough to move them around.
Thank you. So staying on to the topic, what you can measure and how accurate you can measure things. Leila thanks you also for a very nice talk, and she asks, how uncertain is it to quantify the contact angle at the pore scale with these high resolution images? Is it possible to quantify the range of contact angles that you get at that resolution? So what are the error bars on your measurements?
This question goes back, I think it's related to the very first question, where we can identify error bars for these measurements of contact angles. And they are determined in good part by the resolution of the images that you have, and how finely gridded your space is as you're trying to draw these interfaces. We have included part of the measurements in the paper that describes just the algorithm that we constructed to measure these contact angles. But they can range between a couple of percent points to some tens of percent.
So we have so two-part question from Yuang. It's a longer question, so it goes over to message in the chat room. Again, thanking you for a very informative talk. Yuang says, states the contact angle can be measured at the core scale by fitting data to a capillary pressure saturation curve obtained from a core flood. He wonders at the pore and grain scale, it looks quite accurate, but you need these high quality images and good processing. Do you think combining experiments, pore scale and larger scale, would be useful? What are the advantages of combining two different data sets?
That is a great idea. These measurements that I'm presenting at the core scale, yeah, they provide a lot of accuracy and detail, but they're very demanding in terms of time and effort and data analysis. So the proposition that this person is posing is very useful in that if you're able to understand the mapping of the two, the mapping between these pore scale measurements and some more macroscopic observations of capillary pressure curves, by looking at the right correspondence, and that offers an opportunity for extrapolation and be able to use capillary pressure data more effectively in how they inform wettability. I think in principle it sounds like an idea that could be conceived, and maybe even a territory, a domain where tools like machine learning can help significantly, where you have really abundance of data of one type, of one modality, combined with another macroscopic observation that is susceptible to the same variable, wettability and contact angle, and be able to find that correspondence between the two for further extrapolation, and be able to use a cheaper data set to inform the similar type of I think parameter that you're looking for with the pore scale image.
That's great. And as you were sort of answering, there are two questions, pretty much identical questions coming in at the very same time, and they continue on that topic of combining data sets. I pull out Jackson's question here, and Yuan has the same question. Jackson says, nice talk. He's wondering how you quantify and upscale the wettability alteration processes that you observe at the pore scale to the larger scale, the Darcy scale. So how do you take that knowledge that you have from at the pore scale in terms of detailed wettability alteration, contact angle distributions, to make better predictions at the Darcy scale, which is pretty much what Yuan is also asking?
Well, Jackson and Yuan, in my area, I mean, the way to do that connection is through relative permeabilities. I think is the path where we capture the influence of wettability and capillary pressure as well. Where one example is also a piece of work in which I'm collaborating with Dr. Russell Jones, is the idea of creating a model, a better modeling of relative permeability that uses fundamental information that's not only saturation or connectivity, but also contact angles and other parameters that we believe would affect relative permeability in the form of a equation of state. So you can redefine how you describe relative permeability, where we explicitly can incorporate the effect of contact angles, and that would be then the connecting bridge to another scale, where you use pore scale information like contact angle, connectivity, saturation, perhaps surface areas, and to inform a relative permeability that then can be tied to the Darcy models that we work with and that we applied into our reservoir simulations.
Again, so there are some other questions coming on this very topic, but something that kept coming back in my I keep asking myself when I was listening to your talk. So pore scale modeling, network modeling, DNS type approaches are one way to upscale this. You show the contact angle is a critical input parameter in these pore network modeling, digital rock physics approaches. You show this very complex based on pore geometry, the composition of the oil, also on the composition of the brine. So do you think we will ever get, so philosophically, will we ever have enough data to really get the right input data for the pore scale models? Could we get away with a simpler average contact angle, or sort of contact angle distribution in our pore network models. Is there sort of hope for the modeling guys on the end of the digital rock physics spectrum?
Will it ever be enough? It's your question. Yeah. And I think our ambition, shifts as we have access to more and better information. I think we need to build complexity before we can build simplicity. I think then the simpler models are key. The simpler models will allow us to really go through to points of decision making, which is really key at the end application. But to be able to, I think, determine what are the simpler models that are useful and meaningful, we need to dive in complexity to assess the impact of all the parameters that we believe that influence transport porous media. So I think it's key to both work in both directions, but one is not either or. I think they work in combination, whereas as we try to accommodate more of that complexity and we realize, these complexities really have no major impact on the end result, or these complexities are really key on what the outcome manifestation of the process is, that tells us where are the first order parameters that we need to keep track of and which ones we need to measure with greater accuracy. My argument in part here, because I'm measuring contact angles, is that contact angles are important, are really, really important. I believe that it's really one of those first order parameters that dictates, mobility of faces. Pore network modeling, it's one of the techniques as well that allows us to incorporate that richness, that not having necessarily one single contact angle, but having a contact angle distribution. And we've already seen that the response that we obtain in terms of what's the ultimate locus of phase trap that you obtain at different wetting states for the same pore structure can be significantly different. Whether you use a single value of contact angle, you use a more of a diverse range of contact angles, you get to a different endpoint. So a different prediction, a different estimation, a different economic analysis. So it's quite impactful. So yes, we need to dive deep, but always with I think a pathway to kind of collect ourselves and find what are the driving parameters that allow us to have more of the simpler expressions that become more practical.
That's the engineer speaking in you to sort of make things simpler rather than saying this is my sample with my specific quantity.
Make it right, but make it right before you make it simpler, I think, is the point I want to make. I think it's important to make it simple, but you have to make it right first.
Yeah. So here's another really interesting question that Christine is asking, and she wonders, does the flow rate of the injected fluid affect the contact angle distribution? And if so, how would this affect modeling wettability alteration at the Darcy scale?
I would think if you have a uniform rock, if the solid chemistry is uniform across the entire sample, I don't think that the rate of injection would play a major role on what ultimately that state of wettability would be. But I had the impression through these observations and experience in the lab as well, that depending on the flow rate that you impose through your experiment, you're creating a different access and different residence time, and you're creating a different conditions for those interactions that occur between the fluids and the solid. And because of that, I think that the conditions of flow rate may drive changes in the wettabilities that we end up measuring, because you are creating different conditions for the chemical interactions that are happening through the sample. But if everything were to be kind of chemically homogeneous in the rock, I don't think that would play a major role.
Thank you. So time is coming to an end, but there's one more question. Well, it's two questions per one person, and I think you have answered the first one. But Sarah, again, thanking you for the great talk. The first question, I think you have answered this. She wonders, can you elaborate on the role of time in the testing wettability? The second question she had is, can wettability be changed back to the in-situ conditions after they have been altered?
Well, yes, the first question I think has been addressed in the sense that, I mean, these contact angles that we're measuring are static, and we talked a little bit about the effect of flow rate. On the second question, can you bring back the question again?
Of course I can.
For a sec. Yes.
So the second one was, could you change wettability back to the initial conditions after you've altered?
I think we saw in the experiments that we had with the oil, the decanoic oil, we proved the idea of reversibility of those contact angles. So you would have to have a very well calibrated process to truly go back to the original state, but at least that proves the possibility of regressing to a previous state because of that reversibility that was looked at. So we had a rock that was originally water wet, that carbonate rock. We aged it, made it strongly oil wet, and we injected a chemically tuned low salinity brine that shifted those contact angles almost back and similarly to what we had originally.
Great, thank you. Just put up quote from Martin Blunt, just a comment thanking you for the talk and congratulating on the fascinating work and the link to the equation of state RELPERM model. I think, let me echo Martin's comments. Thank you very much for the talk. Absolutely fascinating to peek into the physics that's happening at the pore scale that impact what we observe at the reservoir scale. It's great to see that. Great to see you again, Zuleima, and back to Hadi for some final comments.
Yeah, thank you very much, both of you. Also, we will get the reference to the work, Martin, and post it in the comments after the webinar. And also, we got the hint that Russell should be also on this channel as well. So that's also some good hints as well. I'd like to also take the chance and announce our next week speaker. We are going to host our colleague Sabine den Hartog from Heriot-Watt University. And Sabine is going to present her work on microphysics of fault friction behavior. So it's going to be on the rock mechanics and fault activation, quite a very hot topic here in Europe and across the world, I believe. So until next week, the same time, 4 p.m. European Central, 7 a.m. California, 3 p.m. British time. Stay happy, healthy, and tuned into our channel. And thanks once more, Zuleima, for this extremely nice talk. Thank you very much.
Thank you.
Thank you, Zuleima. Thank you, everyone. Bye-bye.